My name is Emre Tuna, and welcome to the first lecture of the lecture series on Circuit Theory 1, given in the Department of Electrical and Electronics Engineering at Middle East Technical University. Okay. So in this course, clearly we'll be studying circuits. So the first question that I want to ask is, what is a circuit? Or more formally, what is an electrical circuit? Well, we will give a more precise answer to that question soon enough, but at this point, roughly speaking, circuit is what you need to deal with, or what you need to use in order to manipulate electricity. Okay. And there are many applications where we want to manipulate electricity, where we want to use electricity. As we all know, electricity has become an integral part of our modern life. There are many applications, as I said. Some of them one can count as transportation. Electricity is used, and heating and cooling, lighting, and communications, and signal processing, and computation. And I'm sure we can count many others. Okay. So that's what a circuit is, something that we use to manipulate electricity. And then next question is, why circuit theories, or studying circuit theory, is important. Okay. Now there are three motivations. Well, I'm sure there are many other motivations, but I can think of three motivations for studying circuit theory, or studying circuits in general. Well, the first motivation is the obvious one, because, as we just said, through circuits you can manipulate electricity, and electricity is an integral part of our lives. Okay, so that's one motivation. That's usually the main motivation in the engineering department. But there are also other motivations. Another motivation could be, for instance, okay, let me draw a picture. Consider an electrical circuit. Okay, here this is an inductor. Well, we'll all define this later on. Here we have a capacitor and inductor connected in parallel, and then here we have another pair. Okay, so this is two LC oscillators coupled with an inductor. Okay, so this is a circuit. We'll be studying things like that. Of course, we're going to be more precise about what we mean by this symbol, that symbol, and that symbol, so on. Okay, so that's for later. But as for the motivation, this is an electrical circuit. Well, this is a picture of an electrical circuit. And then, now here is a picture of something that's entirely different. Okay. Now this is the electrical world. And now here we have hose. Suppose that this is a pendulum. Okay. And here we have another pendulum. It can swing freely through that hinge. Okay. And then suppose that we connect them by this thing. Well, this picture no longer represents an inductor. This is now a spring. Okay. Now here, this is two mechanical oscillators coupled via a spring, and here we have two electrical LC oscillators coupled by an inductor. So it turns out that, despite the fact that these two things are very different, they belong to different worlds. Okay, this is governed by Newton's law, and this is governed by Maxwell's law. But despite the fact that they're coming from two different worlds, they're described by the same mathematical set of equations. Okay, so that's another motivation. And you can also find other examples from the real world. For instance, you can find a hydraulic network, water networks. Okay, where if you come down the mathematics, they can be represented by circuits. So what I'm trying to say is, here's another motivation for studying electrical circuits, because by understanding them or by developing tools that allows you to understand and design electrical circuits, you will also have, okay, as a byproduct, will develop tools that will be useful in some very different situations. Okay, so that's a second motivation for studying circuit theory, and there's a third, a little bit subjective motivation, and that motivation is that circuit theory has an intrinsic beauty to it. Okay, by that I mean the rules, the building blocks are very simple. The rules that relates those building blocks in circuit theory are very simple, but yet all those simplicity can give rise to quite sophisticated, complex, but by no means arbitrary phenomena. Okay, and that beauty can be taken as a third motivation. Okay, so that's some of the reasons why we study circuits or electrical circuits. Now, let's remember our definition or rough definition of electrical circuit. Electrical circuit is something that you use to manipulate electricity. Now, next question is, what is electricity? Okay, well, we all have an idea of what electricity is, but roughly speaking, electricity is the general term that we use to define phenomena related to either storage or the motion of something called charge, electrical charge. Okay, so therefore the very first definition that we will be starting with is of the electrical charge. Okay, so what a charge is a fundamental conserved property of subatomic particles. Okay, it's measured in coulombs. For instance, the electron has -1 E charge. The proton has a charge of +1 E. And what's this E, or what's its relation to the unit that we wrote down first, coulombs? It's this. E is elementary charge unit. And how it's related to Coulomb is like this: 1.602 times 10 to the minus 19 coulomb approximately. Okay. And then one nice thing about charge is you can bring about certain charged particles, and then you can consider that assembly as a new entity, and you can talk about the charge of that new whole, new entity. Okay, we can talk about the net charge of arbitrary matter. Okay, here's an example. Consider the block. Okay, we have a bunch of particles inside. Okay, 2 neutrons, which are chargeless, 2 protons and 1 electron. You can consider this as an helium atom that has lost one of its electrons, has a net charge of, okay, yeah, +1, these are 0, so they don't count, +1, and -1, so the total makes +1E, okay, 1E charge, or 1.602 times 10 to the minus 19 coulombs of charge is in that block. Okay. What else? Charge is denoted by the letter Q or lowercase q or uppercase Q. Okay. Now, clearly there's no physical difference or mathematical difference whatsoever with what letter you denote the charge. Okay, you can denote it with K, alpha, gamma, B, whatever you want, but there's a historical reason behind this, that we specify the charge with Q, or we specify charge with Q. And that's basically a convention, okay? And we will usually stick to the convention, and one good thing about sticking to convention is that when you communicate with other people, that communication becomes easier if you stick to the same convention. Okay. Another thing I want to point out about speaking of conventions, about using the lowercase and capital letters, also not only for charge but also for other quantities or the other concepts that we will define, like current, voltage, and so on. Usually, there may be some exceptions to it. Usually when we use lowercase letter, it means that the quantity that that letter represents is time varying. Okay, so it changes with respect to time. And whenever we use capital letters, uppercase letters, okay, usually they will be representing quantities. They are constant, okay, with respect to time. So that's the convention that we will adopt in this course. Okay, lowercase and capital letter convention. Okay, so that's all there is to charge, for now at least. Now, having defined charge, we're now allowed, or we can now define something, another concept, another quantity that's quite important for electricity or for circuits, and that next thing is current. Okay, that's our next definition. Okay, incidentally, what we will be doing in this lecture and also in the following lectures is I will present the basic building blocks, okay, the basic concepts associated to circuit theory. We start with charge, now we'll define current, and then comes voltage, power, and so on. And once we have those definitions, then we will list the rules with respect to which these concepts, physical concepts of quantities, are related to one another. Okay? The definitions, then will come the rules, and then once we have the definition and the rules, we basically have all we need to start constructing our theory, circuit theory. And by constructing circuit theory, I mean from the definitions and the rules, we'll try to figure out the consequences, okay, which will be quite interesting. Okay, anyway, so having defined charge, now we can talk about current. Current is basically the rate of flow of net charge. Okay. Rate of flow of net charge. Flow from where? From or through a given area. Okay. So that's given area. It could be the cross section of a wire, for instance, and then You keep track of all the positive charges and negative charges, and then you look at your watch, you keep time, and then you can compute the rate of flow of charge. It's measured given area, okay? It's measured in amps, amperes, by capital A. So therefore 1A should equal, since current is the rate of change of current, and the current is measured by, charge is measured by coulombs, and the time is measured by, for instance, seconds, hence 1N must equal 1 coulomb per second. Okay. And denoted, usually, not always, denoted by the letter I, or the capital I. Okay. Now let's rewrite this sentence in a more compact way. Rate of flow of charge through a given area. So that should mean I of t. Suppose that an area is given, and then t should equal dqt over dt. Okay, the time derivative of charge. Okay, so that's the relation between the current and the charge. Here the current is on the left hand side. If you want charge to be on the left hand side, then you can write the same equation in its integral form. Q of t equals Q0, the initial charge. Suppose that the initial time is 0. From 0 to t, I, tau, d tau. Okay, so that's another way of writing this equation. Okay. Now, this definition is a little bit imprecise if you think about it. So we need not only the area, but also the direction, from left to right or right to left, or from top to bottom or bottom to top. So what I'm trying to say, hopefully, will be clear by the help of the following picture. Okay. So let's first make our definition close to precise, to be able to talk about current. We need a specified direction. Okay. For instance, suppose that we have some component. Well, we talk about components for now, but I'm sure everybody heard about, the voltage source, the current source, or a capacitor, resistor, inductor, something like that. You can suppose that this is a resistor, simple resistor. Okay. And now, this is how we label the points that's connected to some other circuit. And then what we're interested in is the current passing through this wire. Okay. So, in that situation, the given area through which we're measuring current would be the cross section of this wire. Not that, although we draw wires as lines, they have some thickness, physically speaking. Therefore, you can imagine that you're cutting that wire, and then you'll see some area, and then through that area, charges traveling. Okay, from left to right or right to left, and then you count negative charges, positive charges, and you look at your watch, and according to this mathematical formulation, you figure out the current. Okay? So for that, we need a direction. If this, suppose that the direction is given in that, from left to right, like that, and then we apply the definition and you measure something. Okay, let's say 12 amps. Okay. And then clearly, if, for the same situation, if the direction were given the opposite, okay? Then what we would have measured if, suppose that in this case you're measuring 12 amps, if the direction were opposite, what you would have measured would be minus 12 amps, okay? Therefore, A, B, suppose that these two are identical components, then if the direction were given from right to left, then you would have measured minus 12 amps. So therefore, this picture and this picture, okay, they're representing the same thing. Therefore, they are equal. They're equal representations of the same thing. Okay. So that's all we want to say about current for now. Now, we will move on to our next layer, next building block, and it's voltage. So we started with charge, then we defined current, and now we're moving on to a new concept, voltage. Okay. Now consider 2 points. It's a circuit, let's say, that are labeled by X and Y. The work done against the electrical field to move a unit charge 1 coulomb from point Y to point X is what we call the voltage, V subscript XY. Okay. Now it turns out that this work is path independent, is independent of the path through which the charge travels. Okay. If it's path independent, there's only one thing that it can depend to, and it's the beginning and end points. Okay, therefore, voltage only depends on the pair of points through which we're defining it. The charge travels and depends only on endpoints X and Y. Therefore, an immediate consequence of this path independence is Vxy must equal minus Vyx. Okay, which is more or less obvious. Now, voltage is measured in volts. Okay. And V is the letter that we use to indicate volts. And according to this definition, 1 volt must equal 1 joule. Now that joule is the unit that we use to measure work or equivalent energy over coulomb. Okay. So a compact way of that representing that or writing that sentence is voltage equals rate of change of work with respect to charge. Okay. Here W represents work, or sometimes you can take it to be energy. Now, in order to be able to talk about the current, we needed a specified direction. And a similar thing holds also for voltage. To be able to talk about voltage, we need a specified so-called polarity. To be able to talk about voltage, we need a specified polarity. Okay, by which we mean the following example. Okay. A, B, this is some component and it's connected to something, let's say, and let VAB equals minus 12 volts. Okay. So how we describe, how we represent this statement on the picture is as follows. A, you put a plus, for B you put a minus, and then in between you write voltage. Okay, so that's the voltage. Now since VAB equals, okay, since VAB equals minus VBA, this is equivalent to the following representation, A, B. Now you can put plus here and minus there, and if you swap or switch the polarity, what you can do is you have to also negate the voltage. Okay, if it's plus minus 12 volts, then minus plus it's minus minus, which makes plus 12 volts. Okay, this and that, they're telling us the same thing. So that's the business about polarity, about the voltage. Okay. So what we have done so far is we're going through our basic building blocks. We start with charge, and then we let the charge move, and that motion gave us the definition of current. Then now we define the relation of the charge to the work done against the electrical field, and that gave us the definition of voltage. Now let's continue with some other basics of circuit. Okay, our next definition is ground. It's a common reference point for voltage measurements in a circuit. Okay. Given some point X in a circuit, by the X we mean the voltage between point X and the other node that we're calling ground. And that other node is determined by choice. Okay, to be more formal, by Vx we mean Vxg, and this G, this letter, indicates or represents the so-called reference node, reference point. which we call the ground symbol for ground is this. Okay. That is okay, suppose you have a bunch of components connected to one another. This is the circuit, and then you want to measure all the voltages with respect to this reference node. Indicate that that is your reference node, that's your ground. What you do is you draw this symbol attached to that point. Okay, now we can talk about power. Well, before that, let me let's be clear about this V of x. Note that if the ground is not given, then this is ambiguous, because we're talking about the point, the voltage of a point x. Okay? But definition, the very definition of voltage requires 2 points. Okay? So, but this only makes sense if implicitly we have defined, or we have given the ground node, okay, in our circuit. It's very much like talking about the height of the Mount Everest. Okay, note that the height, or the height of the peak of Mount Everest is around 9,000 meters. Okay, but height is certain kind of distance, and to be able to talk about distance, you need 2 points, right? You can talk about distance between 2 points, but what we say is, the height of the peak of Mount Everest is around 9,000 meters. So that's 9,000 meters with respect to something, and that something in that case is the sea level. Okay, so in a sense, this ground, our reference node, is an analog for the sea level for measuring the heights of mountain. Kind of. Okay. Now that's what I want to say about ground. Now let's move on to the next concept, which brings current and voltage in an electrical circuit together. Now here we define power of an electrical component that's part of an electrical circuit. Rate of change of energy. Well, it's a general definition. It doesn't have to belong to electrical circuits. But now for electrical circuits, means something in terms of current and voltage. It's denoted by P, capital P or lowercase p, and measured in watts. Okay, capital W. And 1 watt equals 1 joule per second. Joule is the unit that we measure energy in. Okay. Now P, by definition, is rate of change of energy or work, dW dt. And we've already seen that rate of change of work or energy with respect to charge is voltage. Rate of change of charge with respect to time is current. Okay, this is U of t, this is I of t. Therefore, we can express the power of electrical component simply in terms of its voltage and current. Therefore, we have this very nice relation between power and current and voltage. Okay, so P equals IV or VI. And remember that whenever we talk about voltage, we need to be precise about the polarity. To also, likewise, if I want to talk about current in an unambiguous way, we need a specified direction. Now, using the polarity and direction, we will try to interpret what that component is doing by looking at the sign of its power. Okay. So let's try to be clear about what I just said. Okay. Now here's the so-called passive sign convention that we will stick to in this course. Sign convention. Okay, now according to this convention, which we adopt, that given an electrical component the polarity of voltage and the direction of current are chosen. Okay, so we choose it, and we choose it not arbitrarily, but in a particular way, and that particular way we're calling the passive sign convention, chosen such that the current enters the component from the positively labeled terminal. Okay, the labels that we use to indicate the polarity of the voltage, and leaves from the negatively labeled terminal. So let's be clear about what's writing here on the picture. Okay. Suppose this is our component. Okay. And we want to measure its current, or compute its current and voltage. And in order to be unambiguous about that, what we need to do is we have to choose a direction for the current and polarity of the voltage. And that we can do arbitrarily. But if we want to stick to passive sign convention, we can choose one of them arbitrarily, and once that choice is made, the remaining one must follow automatically. We have no choice left. That is, for instance, suppose we have chosen the polarity of the voltage as plus for the upper terminal and minus for the bottom terminal. Okay, and if that is chosen, such polarity is chosen, then passive sign convention says that we have to choose the direction of the current such that it enters the component from the positive labeled terminal and leaves from the negative labeled terminal. Okay? Therefore, the direction of the current must be like that. Enters from the positive labeled terminal and leaves from the negative labeled terminal. Okay. Now, what's the use of following this convention? Here is the use according our convention. Okay. Suppose you follow our convention and you compute the current and voltage, or you measure the current and voltage of this component, and then you computed the power, which we said is the product of those two, the current and voltage. And then the sign of that power tells you generally what this component is doing, in the sense that whether it's absorbing energy from the circuit or it's delivering energy to the circuit that is part of it. And the rule is as follows: if P of t, the power of this component, which is IT times Vt, at some time t is positive, okay, it means that then the component is absorbing electrical power. Okay. Example, your toaster. Okay, you put your bread in it and you press the button, and if you compute the current and voltage for that toaster, you'll see that at any given time the product is always positive. That is what the toaster does is it absorbs electrical power from the network and it transforms it into the heat, okay, some other type of power. If on the other hand, opposite is the case, that is if PT, power at some given time is negative, it means that whatever that component is, it's giving energy to the circuit that is part of at that particular time t. Then component is delivering power. Okay. An obvious example would be battery. Okay. Of your wristwatch, for instance. Okay. So what we have covered so far is we talked about charge, then we talked about current, we talked about voltage, okay, and we mentioned how we should be careful about current measurements, about the direction and also the polarity in voltage measurements, okay, and then we talked about the passive sign convention and what it means if you obey the passive sign convention, when the power is positive and when the power is negative. Now, these are the first set of basic definitions of quantities that we'll be working with. Okay. Now, what we'll be doing in this course generally is, given a circuit, we will try to solve that circuit. Okay, we'll do some other stuff too, but basically that will be our main goal. Given a circuit, we have to solve the circuit. And what do we mean by solving a circuit? Generally speaking, solving a circuit means figuring out all the currents and voltages of all the components in the circuit. Okay. For that, we need to make certain assumptions to simplify life, and the assumptions that will simplify our computations, but will not hurt us from the accuracy point of view, are the following. In this course, we make the following assumptions. Okay. Assumption 1, electrical effects happen instantaneously throughout the circuit. Okay, that's our first assumption. Now, this is not a precise statement, but what we mean by that is the following. Suppose that there's an electrical switch here, okay, which I'm using to turn the light on or off. Okay. Now, there's a finite time between the instant that I touch the switch to turn the light on and the instant that the light actually turns on. That is, the instant that the light feels that I touched the switch. Okay? But the distance between those two instances are so tiny that we can suppose that the difference is zero. And roughly speaking, that's what we mean by electrical effects happen instantaneously throughout the circuit. Okay, so that's one thing. A2, and that assumption is okay. Before I state A2, let me talk about A1. Just say one thing about A1 too. That assumption is quite a valid assumption because the instance, such difference between those two instances are very small in general. Okay, but there are, you can imagine some situations where, for instance, the transmission lines, where distance between 2 points in your huge circuit is about, let's say, 1,000 kilometers. So when you're talking about in the order of 1,000 kilometers, then this assumption may not be valid to work with. Okay, but generally speaking, if the circuit is small enough, then this assumption is quite satisfactory to work with. Now, the second assumption is the following: the net charge inside any closed surface is always zero. Okay. Now, these are the assumptions under which we will study electrical circuits. And now although we talked about what we mean by a circuit, now we're at the point where we can give a slightly more accurate definition of it. Okay. Circuit or electric circuit. So it's interconnection of basic electrical components. And those basic electrical components we will define soon enough, we'll talk about soon enough. Circuits that let us make or for which making the first assumption is reasonable, A1, are called lumped circuits. Okay. So, and in this course we'll be dealing with lumped circuits, and lumped circuits generally means a small circuit. Well, I'm talking about physical size, okay, so small circuit. And that's roughly what electric circuit is. And in this course, we'll make heavy use of schematic representations, or more simply, we'll make heavy use of pictures. So they'll be of great help to describe and also study circuits. And those pictures will look like the following. Okay. For instance, here we have a component. Here we have, then it's connected to another component, and then they are connected to yet another component. And here we have a component that looks slightly different than the first three, because it has 3 wires sticking out of it. Okay. And then that thing is connected to this point here. Okay. So here we see a connection of 1, 2, 3, 4 components, and this thing is how a circuit looks like. Okay. Well, a picture of a representation of a circuit looks like. Now, this thing, where 2 terminals meet, terminals of a component, is what we'll be calling a node. Okay, so this is a node, this is a node, this is a node, and that's a node. And then suppose we draw this separately by terminal. Meaning each of the wires that are sticking out of our component, so that's a terminal. And this thing is a 2-terminal component because it has 2 wires sticking out of it, like a resistor, like a battery, okay, or like an inductor. 2-terminal element. Sometimes 2-terminal elements are called single branch elements, and that the word branch we will use once we study circuits from the graph theory point of view. So this is also called a single branch element. Okay. And this thing, if we draw it separately, is a 3-terminal element. Okay. And finally, let me squeeze the definition of a node here. And a node is point where 2 or more terminals meet. Okay. So in this circuit we have 1, 2, 3, 4 nodes. Okay. So this is the end of our first lecture, in which we covered some very basic definitions. We started from charge, then we defined current, and we talked about voltage. We defined the power of an electrical component, which was simply the product of current and voltage of that component. We talked about passive sign convention and what happens if you obey to passive sign convention, how we can interpret the sign of the power, okay, if you obey passive sign convention. And we mentioned the assumptions under which we'll be working in this course, and lastly we provided some descriptions some definitions regarding the pictorial description of a circuit. Okay. In our next lecture, we will get closer to develop techniques in order to solve a circuit. Okay. And to solve a circuit, once again, generally means, at least in this course, is given a circuit, figuring out all the currents and voltages associated to every component. Okay, so suppose we have a circuit and composed of only two-terminal elements. Okay, let's forget about that three-terminal element. We have 10 such components, each two-terminal, and each two-terminal element means one voltage and one current. And we have 10 such elements, so that makes 10 voltages and 10 currents. Okay, so a total of 20 unknowns. Therefore, what we require is we have to figure out 20 equations in order to be able to obtain, in order to be able to solve that circuit. Now, exactly half of those equations will be coming from the so-called network laws, and the remaining half will be coming from the so-called terminal equations. Okay? And those two things will be what we will be talking about in our next lecture, namely the network laws, also called Kirchhoff's current law and Kirchhoff's voltage law, okay, and also the terminal equations. That will be the subject of lecture 2. Okay, that's all.